All right, well, I'm starting the recorder, but OBS, the preview is on the wrong part of the screen. I'm not exactly sure why, but I think it's still recording correctly. So let's go ahead and, well, we still have about a minute or so before it gets started here. Let me see if I can fix OBS. All right. Oh, if you guys don't want the sun beating on you, you can kind of close the blind if you want to. Nope, doesn't bother you. Okay. I might just close this one because it's on the screen. Just close this one, and you have control over that one if you want to. All right. All right. So I think I'm gonna get started, even though OBS is not displaying the screen they're supposed to be recording, but when I checked it, it's still on the right screen, so I think it's gonna be okay. All right. So what we'll do today is to start with Pascal's identity. Unless I'm forgetting about something, I think this is the next topic. So did anyone have a chance to read Pascal's identity and how it's proved or how it's proven? Maybe not. Okay, that's okay. We'll go ahead and get started on this one because the one topic before is a coin toss. Maybe we'll start with the coin toss problem first. All right, so we'll start with the coin toss problem. Um, if I toss a coin 5 times, same coin, what are the chances that there are 3 heads and 2 tails? Okay, so that's the first question. Um, how do I figure out the answer to that question? How would you do it? Do you remember the tree approach? And if you do remember the tree approach, how would that help you to get to the answer of this question? And also on top of that, am I forgetting to tell you something to actually figure out this probability? So all of those are things that I want you to kind of think about because um, that's how we can learn about the really important concepts. And this has to do with the binomial distribution, but we are not quite there yet. Okay, so we are not referring to this as binomial distribution. So we'll start with just that. If I toss a coin 5 times, what are the chances that there are 3 heads and 2 tails within those 5 tosses? So the first thing is you kind of have to make an assumption. If I don't tell you ahead of time and I don't say anything about it, you kind of have to make the assumption that the chances of landing on the head versus the chances of landing on the tail are the same. So it's a 50-50% kind of chance. Is that okay? Now it doesn't have to be. So later on we'll talk about what to do when you have a loaded coin, where it's lopsided, 60-40%, 55-45%. So for now we'll make that assumption. So the second thing we also want to know is how do we present this particular problem using the terminology that we are already familiar with. So the first thing is we have to identify what is a trial. So a trial is a term to refer to one particular action that is individual. In other words, we cannot break that one step down any further, and it has a particular set of possible outcomes. Is that okay? So flipping a coin It's a trial because you cannot break flipping a coin into smaller steps, and it definitely has two finite possible outcomes. Either it lands on the head or it lands on the tail. Is that okay? So one trial is flipping a coin once. So in that context, an experiment in this case is the sequence of flipping a coin 5 times. All right? So now, given all of those, the first thing we want to look at is omega. In other words, we look at the entire experiment of flipping a coin 5 times. The question is, how many ways can we, how many possible outcomes can we expect out of the entire experiment? So what if I'm just interested in the cardinality of omega, what would that be? That should be it. Go ahead. Hmm? 2 to the fifth. That is correct. 2 to the power of 5 is the answer. And why is that the case?
For each trial, there's 2 outcomes after 5 trials. I'm just picturing the tree, and then you can multiply.
Exactly. So the key word here is for each trial, there are 2 possible outcomes. But for each outcome of that trial, it leads to more trials. Okay, but the key word is for each, because that tells us that we have to multiply instead of add. Okay, so that is correct. So what I'll do next is I am going to go to Zernal. Okay, I'm going to change my Zernal screen. Okay, maybe add a new page. Give me a second here. There we go. And now I can draw a picture of the 5 coin tosses. Okay, so we're going to say that we're going to start here. This is the starting point. This is before the first trial. So the first trial will end up with 2 possible outcomes. So we can end up with a head or a tail after the first trial. Okay? But then the second trial is going to look like this, right? The second trial will look like this. We have a head after a head, or we can have a tail after a head. We can have a head after a tail, or we can have a tail after a tail. What about the third trial? Well, the third trial is going to look like this. What about the fourth trial? Split even more. Okay. Oops. Like that. And you can see after the fifth trial, we have the 32 possible outcomes. So now we're splitting even more like that. So this is good for counting, but it's not going to be very good for actually displaying the 32 possible outcomes. Okay, and just a few more, we're done now. Okay, so every single leaf node at the very end or on the right-hand side is representing a possible outcome for flipping a coin 5 times. And this is also why there are 32 of them. Are we okay so far that there are 32 possible outcomes? Okay. So then now the question is, I'm not interested in all 32 outcomes. I'm only interested in the ones that end up with, according to the module, I'm only interested in the ones that end up with 3 heads and 2 tails. So the question is, how do we count those? Tak, you have not taught us any skills to count the number of trials that end up with 3 heads and 2 tails. So this is where we see a little bit of an interesting problem, is if I look at this as 3 heads and 2 tails, and looking at the omega, using all 5 trials, that's one way to look at it. The other way to look at this is to ask, well, out of 3 heads and 2 tails, what can be the possible positions of the 3 heads within the 5 trials? Okay, so let me describe what I mean by that. Let me switch back to Zerno++. Okay. Oh, that's not it. Zerno++ is this one. There we go. So I'm going to look at each one. I'm going to look at two of those, and then I will talk about how to encode those two particular outcomes. So the first one is, okay, let's try head, head, tail, head, tail. Okay? So when you look at this particular experiment outcome, it does meet the requirement that we want, right? It has exactly 3 heads and 2 tails out of 5 trials. Is that okay? So now we'll look at another possible outcome, which is head, tail, tail, head, head. Okay. So do we all agree that these are two possible outcomes out of flipping a coin 5 times, and it meets the requirement of 3 heads and 2 tails? So this is one way to encode it, okay? One way to express the outcome of the experiment. But I'm going to propose a different way to express the same thing, okay? I'm going to use the position of the head, which is position 0, position 1, and this is position 3. This one is position 0, position 3, and position 4. Is that okay? So now I'm going to encode the first one as a set, which has 0, 1, 3 in it. I'm going to encode the second one as a set that has 0, 3, and 4 in it. Is that okay? So what this is illustrating is basically to say, if I want to encode the outcome of flipping a coin 5 times, one way to look at it is really just to list out, okay, where we have the head, where we have the tail. But the second way to do it is to use a set, okay, to basically list the position of the trials where we end up with a head. Are we doing okay so far with that? I changed it from a sequence encoding, which is a tuple, because when you look at HTTHH, that is a 5 tuple. It is a tuple where if you change the positioning of something, it becomes something that is different. So instead of using a sequence, a tuple, a 5 tuple in this case, to represent one specific outcome, I'm changing that notation to use a set notation. What is each element of the set? It is representing the position of the head of a trial that ends up with a head. Is that okay? So you guys would now be asking, so how is that going to help us to count the number of outcomes that meet the requirement of 3 heads and 2 tails? So I'm going to pause a little bit because I want you guys to think about it, okay? Think about all the things that we have learned up to this point. And then you ask, what type of technique is going to help? Yes?
It's kind of like a function. So, you can say like 0, like there can't be any matching part. So it can't be 0, 0, 0. That's not a valid set.
That is correct.
So it can be like 0, 1, 2, 0, 1, 3, 0, 1, 4, and 0, 1, 5. So then that's how you solve for 0, 1.
There's no 5 because 4 is the last one. But
oh, sorry, my brain's thinking of.
That's okay.
Yeah, it starts with 0. So yeah, 0 to 4 in each location. But they can't match.
Right. They cannot be the same.
Exactly.
Okay, so if they cannot be the same, haven't we kind of encountered something like that where you cannot have duplicate items, despite, I'm just kind of getting some items out of a pool of items? Does that remind you of Lotto in any way? Because in Lotto, we have 69 possible numbers. We only want to pick 5 of those, right? So in this case, we have 5 numbers to begin with, 0, 1, 2, 3, 4, and we want to pick 3 of those. Does that make sense? Okay? So in other words, I am basically transforming the problem from a coin flipping problem to grabbing numbers out of a bag kind of problem. Because now I have a bag that has the 5 numbers in it, 0, 1, 2, 3, 4. And my job is to pick 3 things out of those, 3 items out of the bag. But every time I pick something out, I am not going to put something back in. Is that okay? And ordering is not important. Okay, because we're dealing with a set here, so that means that 430, 304, 430, and they're all considered to be the same. Is that okay? So are we dealing with combination or are we dealing with permutation?
Combination.
We're dealing with combination, and in combination, how do we figure out the number of combinations in this case? It would be represented as 5 choose 3, okay? So if you look at the whiteboard or the projector, it is represented as 5 choose 3. Um, Great, but that doesn't tell me how to do the computation. I mean, you can enter this as combin 5 comma 3 in a spreadsheet. The spreadsheet will do the calculation for you. But if I want to do this calculation by hand, what is that going to look like? So what you need to do is to look up the combination formula and then just plug it in. So this actually boils down to 5 factorial divided by 3 factorial times 5 minus 3, the whole thing factorial, which is basically just 2 factorial. So 5 factorial is 120, 3 factorial is 6, 2 factorial is just 2. So that means there are 10 exact ways to end up with 3 heads and 2 tails in 5 coin tosses. Okay, so I'm going to pause because it would seem that I'm mixing up 2 different concepts together. Because if you look at it from the perspective of a coin toss problem, then we have the same 2 possible outcomes regardless of which trial we are in, and then ordering is important. But on the other hand, if I transform this into taking 3 numbers out of a bag with 5 numbers, then it is a different problem because now I'm using a problem that is without replacement, and also ordering does not become important anymore. So are we still relating those 2 things and understanding how they connect? Okay, all right. So great. So we know there are 10 ways to end up with 3 heads and 2 tails in 5 coin tosses. But we also know altogether there are 32 ways to end up from an experiment that has 5 coin tosses. So what is the probability to end up with 3 heads and 2 tails in this case? So let me kind of write this down here. The cardinality of omega is 2 to the power of 5, which is 32. The 10 is representing the number of things that I want. The 32 is representing the number of things that can potentially happen. So the question is, what is the likelihood of something that I want actually happens? How do we calculate that? 10 out of 32. Very good. So the probability is really just looking at the things or the number of items that I want, that is of interest to me, and divided by the number of things that can potentially happen. So that's about 1/3. Is that okay? All right. So why would I care? Why do I care about the probability of something like this? Because has anyone heard of um, self-correcting code? Okay, there are ways to transmit a packet where it can quote unquote self-correct. Okay, it can detect which bit is wrong and then it can fix it. So in those cases, let's just say that out of a packet of 1024 bits, I can afford to have 2 bits that are transmitted incorrectly. Okay, that's just an assumption. So I can now ask, if I know the probability of each bit arriving and being received correctly, I can now I can now calculate the probability of not needing to retransmit a packet. Does that make sense? So then the question becomes, why do I care about the probability that I do not need to retransmit a packet? Why would that be important? And you're all going like, well, I cannot think of a practical reason why this is important. So think of this scenario. Your Wi-Fi router is all the way over there. Your gaming computer is all the way over here. And somewhere along this straight line is a microwave oven. Okay, and this is back in the old days when we do not have 5 gigahertz of frequency. There's only the 2.4 gigahertz for Wi-Fi communication. Okay, first of all, how are these dots connecting? Okay. Has anyone actually experienced this problem, anytime within your life where you're on an online game and then somebody, mom is cooking something or heating up tea, and then suddenly you lost connection to your game? Yes?
I have a friend who had their router and then the microwave just happened to be directly in between them in the room.
Yep. And then what happened?
They just die every time the microwave.
Yes, exactly. So the question is, okay, there are a few things, okay? There are questions that are unrelated to this class. It's like, why is 2.4 gigahertz even important? Because that's microwave, okay? Your microwave oven, uses a kind of wider, spectrum spread, but 2.4 gigahertz is right within that spread, okay? In other words, okay, in simpler terms, your microwave is a very strong source of something around 2.4 gigahertz. It can interfere with the old Wi-Fi standard, okay? So if your microwave is sitting right between the Wi-Fi router and the gaming computer, and your gaming computer is using Wi-Fi communication, every time you use the microwave, I don't really care how careful they are to shield the frequency, because you don't want your microwave oven to be unshielded, because then all the microwave energy is going to radiate out of the microwave oven. So in addition to heating up the food, it will also heat up all the people around the microwave oven, which may not be a very desirable outcome of using a microwave oven. But it still leaks, okay? Even though you have all of these protection mechanisms, it still leaks a significant amount of microwave energy out of the oven. So now it's going to interfere with your Wi-Fi router. And this is why this kind of calculation is important. Because you want to, if possible, you want to be able to say, okay, if the probability of receiving a bit incorrectly is high enough, I'm not even going to go start a game when I know some people will be using the microwave oven. Is that making any sense? Because you have to kind of determine, is it tolerable, okay? If that probability exists, but it's not really that high, you go like, okay, maybe it would just kind of slow down my reaction time a little bit in this game, but it will still be playable. On the other hand, if the chances of your packet getting corrupted is really high, then you go like, okay, I'm not even going to bother to play because it's not going to work. Okay, so this is of course, this is a made-up scenario, but there are other scenarios in real world where there's a probability associated with receiving a bit correctly or not. So can someone give me a application where that probability is important? It is not a very small number. It is variable in many, many ways. Microwave communication, between buildings and stuff like that. How often do you need a repeater when you're dealing with, networking? Because every time you have a repeater, you're basically re-amplifying the signal. So you're recovering the kind of degrading signal and you're regenerating the signal from scratch, so it's nice and fresh again. So networking, application can potentially use the math that we are talking about, because they can now calculate and they can model the chances of a packet not being received correctly. Is that okay? All right. Now, what does this have anything to do with TCP/IP? I should say, what is the importance of this, in terms of TCP versus UDP? I know this is not a networking class. I never teach a networking class. But does anyone know what is TCP versus what is UDP? Go ahead.
TCP is more important information, so it has stuff has to be sent in order, and if something is sent incorrectly, it has to be resent.
Mm-hmm.
But UDP is more of a just fire all of it, and if some of it doesn't make it, then it's okay
Mm-hmm.
kind of method.
Yep, exactly. So if you're using TCP and there's a problem, somewhere along the line, the mechanism will try to retransmit. Okay, it will try to maintain everything being receiving in order and received correctly. That's TCP. UDP is more like, okay, this is what I want to send, and that's it. After I send it, I'm going to assume, well, the program can assume the other side is getting it. So if you're working in a noisy type of environment, TCP can still kind of get things going, but it will impact the speed of the transmission. UDP, on the other hand, you can lose an entire packet and not know about it. Is that okay? So once again, it boils down to, well, what are the probabilities of this happening? Is it worth risking it, or do we know the probability is high enough that I have to build in some kind of error checking, timeout, and other types of mechanism, so that if I transmit a packet, a UDP packet, and I don't hear back anything, I'm going to say, maybe the other side did not get this. Let me resend it with another packet, or do something about it. All right. Are we doing okay so far with these concepts? All right. So we are going to switch to, we're going to take a look at this equation here. So in this equation, P is representing the probability of landing on the head. Q, which is 1 minus P, is representing the probability of landing on the tail. Is that okay so far? All right. So if I use your P plus Q, the whole thing you raise to the power of 5, let's ignore this side here. Just look at this one here. What does that have anything to do with what we just did? So let's go back to the picture that I drew earlier. Okay, so I'm going to switch back to here. So what we'll do this time is we are going to associate a probability on each branch. So this is going to be P, this is going to be Q, okay? Because P is the probability of ending up with a head, and then Q is the probability of ending with a tail. Is that okay? So what happens to the second trial? So we have another P here, we have a Q over here, another P here, and a Q over here. And what about the third trial? Well, same thing. P, Q, P, Q, P, Q, PQ, like that, okay? And what of the fourth trial? The same deal. What of the fifth trial? The same deal. So this means if I want to know the probability of one particular leaf node on this side, all I have to do is to multiply all the numbers in between. That will give me the discrete probability of ending at a very specific leaf node. Is that okay? But I want to sum up all the leaf nodes with 3 heads and 2 tails. So the question is, we know how many there are, right? Because if we just calculate that it is 5, 2, 3, we also know that along that path, there'll be 3 P's and 2 Q's. Is that okay? So that means the probability, if I know what P is, which automatically means that I know what Q is, so that means given P and Q, the probability is now modified just a little bit, because now it is modified to be P, okay, I should say 5 choose 3 times P to the power of 3 times Q to the power of 2. So this probability here is applicable when you say, well, the coin is even, okay? The chances of landing on the head and the tail are exactly the same. It's 0.5 in both cases. In that case, this will work. All you have to do is count. Simple, right? On the other hand, if the probability of landing on the head versus the probability of landing on the tail are different, then this approach is not going to help you that much anymore, right? Because this one is just counting. But the other one will be much more helpful. The probability is 5 choose 3 times p to the power of 3 times q to the power of 2. Q is just 1 minus p, by the way. Is that okay? All right? So given that is the case, if I switch back to the browser, um, then if I want to look at every single possible outcome, then the summation is going to capture every single one, because what I is representing is how many heads are we talking about. So when I equals to 0, I'm basically asking, what are the chances that out of 5 coin tosses, we have 0 head and 5 tails? That's what I being equal to 0 is representing. I being 5 is representing the other extreme, which is asking, what is the probability if I have 5 tosses, all 5 ends up with heads, and none would end up with tails? Okay? So the question is, what is the coefficient to use here for k of I? So that is the question. Is that okay so far? All right. So the other way to look at this, okay, another way to look at this, to link this whole concept to something else that you already have exposure to, but you probably were not thinking, I didn't know it relates to what we are talking about here. Let's ignore this sign here. We'll just focus on p plus q to the power of 5. You go like, so, well, let me switch back to Zernal. You probably know what this is, right? Okay, because when 5 is 2, we have a binomial, right? And then, but you can figure out, what this whole thing expands to. Okay, do you guys still remember how to expand 1 plus x to the power of 5? Sort of, maybe? Okay, so let's go ahead and do this, okay? So we know this ends up with a 1 plus some number times x plus some number times x squared plus number times x cubed plus some number times x to the power 4th plus some number times x to the power 5. We know this is okay already. We know there's only 1 of x to the power 5, right? Because when you multiply 1 times x to itself 5 times, there's only one sequence to only choose x every single time out of the 5 numbers of the 5 terms that we're multiplying, right? How do you figure out this term over here? And this one, and this one, and this one over here? In other words, I'm asking, how do you know this is supposed to be 5, this is supposed to be 10, this is supposed to be 10, this is supposed to be 5? I mean, you can,
Pascal's triangle.
Pascal's triangle, very good, okay? Does everybody know what is Pascal's triangle? No? Okay, that's fine. I will introduce Pascal's triangle. So Pascal's triangle is a triangle, and I'm going to draw it like a real triangle right now, but later on I'll skew it a little bit so it doesn't look like a how should I put it? This is not lopsided, okay? But later on I'll draw it in a way that is lopsided. So the third line is going to be 1, 2, 1, 1, 3, 3, 1. So for those of you who do not know what is a Pascal's triangle, because for those of you who didn't know what is a Pascal's triangle, you already know what number goes here. But even if you have no exposure to Pascal's triangle whatsoever, if I spell out the first 4 rows right here, can you say what is going to go here? Do you see a pattern? What's going to go there? 4, okay. And what is going to go here? 6, and then here? 4 again, and then the 1 here, and then on the next row, what do we get? 1, and then 10, 10, 5, 1. What is the pattern? The pattern is a number, the value of a particular place is the sum of the 2 numbers on top of it. Well, I shouldn't say exactly on top because they're staggered. So this 5 is the sum of the 1 and the 4. This 10 is the sum of the 4 and the 6. and so on. And then somebody is going to complain and say, but Tech, this is very inelegant. Because what happens to the ones? You cannot explain the ones, can you? And I can go like, yes, I can explain the ones. Imagine this triangle is in a sea of zeros. The empty space are zeros. So if the empty space are all zeros, and I'm concerned about the value that goes here, that means there's an implicit zero over here. 0 plus 1 is a 1. Okay? So all you have to do is to basically say everywhere else, they're all zeros. Okay? So now every single cell is truly the sum of the two numbers on top of it. The only one number that cannot be, that has to be assumed is the very one all the way on top of the triangle. That's the only thing you need to know. The rest can be done by using that rule of a particular value of a cell is the sum of the two numbers on top of it. Because there's a zero implicit here, implicit zero over here, and another implicit zero over here. So that means this one here is the only seed that you need to work out the rest of the numbers. Are we still doing okay so far? Are we comfortable with Pascal's triangle at this point? Okay. So now we have a few concepts that are all kind of sort of unrelated. They're independent, and now I'm kind of putting them all together. So the question now is, okay, I can sort of see how Pascal's triangle is relevant in the problem, in the artificial problem that I made for myself, which is 1 plus x to the power of 5. What if I change the 1 to p, and what if I change the x to q? All right. So if I change the p x to, if I change 1 to p and I change x to q, then we end up with p plus q to the power of 5. So this way I can figure out how many times do we end up with only one x, which is q, but that is implicit to have 4 p's. Is that okay? So that is basically the same thing. What you know about what you know about binomials is directly applicable to what the problem that we're trying to solve here. And then the coefficient or the constant for each term is coming straight out of Pascal's triangle. Are we still doing okay? But somebody's going to say, but Tech, that means if I need to figure out, let's say, p plus q to the power of 20, I am going to have to work out Pascal's triangle up to the 21st row, which is going to be, it's going to be tedious. Is there a way to get to the numbers on that particular row for p plus q to the power of 20 without having to work out this entire table? Because this is cool, but it's tedious. So that becomes the next question. Okay? And that's the one thing that relates to what we are going to talk about today, as well as something that we have talked about already from the past. So I'm just setting up the context of what I'll be talking about next. So if I switch back to the notes here, the first thing we're going to talk about is what we call Pascal's identity. So this is Pascal's identity. Pascal's identity is basically saying n choose k plus n choose k minus 1 is n plus 1 choose k. That's basically what it is trying to state. Everything in between is a derivation. It's simply, me doing the proof step by step using just algebra. So I'm going to go through the proof first because I do think that we should be able to derive this particular equation. So we'll start with the first row, okay, which is right here. So what is happening on the first row? How do I get from the left-hand side to the right-hand side? That's just using the definition of. Tell me again, what is the notation when I use parentheses like this? What is that notation? It's trying to combination. or otherwise the short way to say that is choosing. So it's n choose k, and then the other one is n choose k minus 1. By definition, n choose k is expanding to n factorial divided by k factorial times n minus k, the whole thing factorial. That's the definition of combination. Is that okay? So the first row is really just using the definition of choosing or the number of combinations. And then from the first row to the second row, what did I do from the first? What is the change from the first row to the second row? Not yet. So what I did was to use the associative law in algebra. So I just moved the subtraction of 1 all the way. Um, oh, the minus subtraction of 1 becomes an add 1. And then the subtraction of k minus 1, I extract the k, so I move the k on the other side. In other words, all I did was to move around the parentheses a little bit, and that's how I got from the first row to the second row. All right, so what about between the second row and the third row? What am I doing between these two? We can see I did something that changed both the numerator as well as the denominator of the right-hand side of the addition. In other words, it's about this one here. But what exactly did I do? I multiply both by k. That's right, okay? Because effectively, I'm just multiplying the original thing by k divided by k, which is 1, which doesn't really change the value. All right, from here to here, what did I do? This one is a little bit trickier. It's not in the normal algebra sense, but when we understand factorial, this one is not too bad. So what did I do from here to here? You can see the left-hand side of the addition is unchanged, but all the changes are on the right-hand side of the addition. So what did I do from here to here? Tell me again what is n minus k plus 1, the whole thing factorial. It is n minus k plus 1 times n minus k times n minus k minus 1, blah, 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 right? So what I did was I separated the first item from the rest of the item. So n plus k plus 1 factorial has an n minus k plus 1. I broke that piece out of the factorial. And then the rest is just n minus k factorial. Is that okay? So the piece that I broke away becomes the denominator for just the numerator itself. That's just algebra, right? Is that okay? So that's all I did from the third to the fourth row. What about from the fourth row to the fifth row? The right-hand side of the addition stays the same, and I'm doing something to the left-hand side of the addition. So what did I do? How did I change from n factorial to something that is just a lot more complicated, but it means the same thing? I multiply the whole thing by
N minus k plus 1 over n minus k plus 1.
exactly. So it seems to be pretty meaningless. I mean, I preserved the value and all, but it seems to be just, oh, you're just making it more complicated for no reason. Well, there's a reason why I did that. Because now, if you just look at um, the denominator of the numerator combined with the denominator itself, they're both the same now. In other words, both are now m minus k plus 1 times k factorial times n minus k factorial. So that means now I can combine. I have a common denominator, so the numerator can now be added. So that's why this is what allows me to move this addition into here, which means I'm adding the numerator because they share the same common denominator. Is that part okay? Okay. And then from this row to this row here, what did I do? Well, there are two things that I did, but neither one is very profound. So I move this denominator of the numerator down to the denominator itself. So n minus k plus 1 becomes a term of the overall denominator. But I also did one thing, to the numerator. I used distribution. So n factorial times n plus 1 becomes n plus 1 factorial. N factorial times k becomes n factorial times k. And then this n factorial times k is what's coming from before. So I'll be doing okay in terms of the algebra, going from this one, which is the 5th row, to the 6th row. Yes? Okay. And now we cancel out these two because we have a subtraction of n factorial times k, and then we added back the same amount. So we just say, that's just cancel out, no problem. So that's how we got from the 4th last line to the 3rd last line. So now from here to here, what did I do? This is just the same kind of trick that I did earlier. I look at n minus k plus 1, and I rewrote it as n minus n plus 1, the whole thing, minus k. So are we still doing okay with this? How this particular expression, n minus k plus 1, is really the same thing as n plus 1, the whole thing, minus k. Why is that important? Because now when we look at the last form here, it also fits the pattern of n plus 1 choose k. Because n plus 1 choose k is n plus 1 the whole thing factorial divided by k factorial times n plus 1 the whole thing minus k factorial. So that's how I can come to the last line, which is the conclusion, which is n plus 1 choose k. Is that okay? So this is mostly just algebra. The only tricky part of this, proof is to make use of the, I would call this the accordion effect of factorial. Okay, you can basically peel off one thing, separate it from the rest, but the rest of the accordion is still an accordion. Okay, so that's the only trick, in this entire proof. All right. So the next thing we have to do is to prove the binomial theorem. So the binomial theorem is to say that this particular statement is true. Okay, as long as n is a natural number, p plus q to the power of n is the same thing as the summation of I going from 0 to n. Each term that we are adding in this sigma notation is n choose I times p to the power of I times q to the power of n minus I to q to the power of n minus I. Okay. Is that okay? This is what we want to prove. And for some reason, this has something to do with Pascal's identity. Wait, Pascal's identity and Pascal's triangle, are those two things related? And if so, how are they related? So let's answer those two questions first. First of all, are they related? I would think so, okay? Pascal's triangle versus Pascal's identity. Let's just say that they're related. So number two, the second question is, how are they related? They're completely different. I mean, look at this. Look at this tag. This is just for adding stuff. So every single row, every cell is the sum of the item right before it. And then we look at Pascal's identity. We go like, that has to do with the calculation of the number of combinations. They're entirely different things. How can these things be related? What do you think? If I tell you ahead of time that these two things are related, how would you figure out the relationship between those two things? In other words, okay, the first thing I notice is the addition, okay? Because in Pascal's triangle, each cell is the sum of the two numbers on top of it. And in this case, this thing here is the sum of these two things, okay? So that will give me the first clue as to how these two concepts are related. Second thing is, what is the first number in the choose? What is this n plus 1, and what is that n over here? What do you think? One is one more than the other one. So when you look at Pascal's triangle, we are looking at row numbers, right? So we'll call this row number 0. This is row number 1, row number 2, row number 3, row number 4, row number 5. These are the row numbers. So, okay, if I look at those things, if I look at the row numbers, it would seem that the row, I can use something from this particular row to figure out a value of the next row, right? So let me give you a very concrete example. If I need to figure out this particular value over here, which is on row 6, right? So on row 6, this particular value is the sum, oh, that's the addition of these two numbers, and these two are adjacent. Is that okay? So I can now figure out this is 15. Are we good so far? So it would appear that in a combination, what we are choosing from has something to do with the row number. So now what is the other number? What is the second number telling us?
The position within the row.
The position within a row. That's it. Okay? So that means, okay, so if I were to use a different color, because I think it's better this way, this is 0, 0, okay, because it's on row 0 and it's also at position 0. This one here is on row 1, position 0, and this is position 1. This is on row 2, position 0, position 1, position 2. This is on row 3, position 0, position 1, position 2, position 3, and so on. Are we doing okay so far? Okay. So that means if we look at it from the perspective of a choose representation, this is our row number. This is our column number within that row. And both are 0 oriented. In other words, we count the rows from 0. We also count the columns from 0. The rows are counted from top to bottom. The columns are counted from left to right. Is that okay? You guys are looking at this and go like, I don't think so, Tack. Let's prove this, okay? What about this 15 here, okay? What is it corresponding to? So this 15 is corresponding to row 6, right? And it's corresponding to position 0, 1, 2. So I'm now claiming that 6 choose 2 should be 15. Or the number of combinations of choosing 2 things out of 6 should be 15. Are we doing okay so far? This is a conjecture. This is I'm suggesting that if my theory was right, then 6 choose 2 should be 15. How do we know?
Plug it in.
Plug it in. Very good. Okay. That sounds like a commercial from some aromatic product that plugs into the wall outlet. Pretty sure it's trademarked. I don't think Google is going to complain that I upload a video with that slogan mark in it. Maybe one day. All right, so let's expand this, okay? What is 6 choose 2? If I were to figure out the value of the number of combinations of choosing 2 items out of, and it does say scam likely. So this is 6 factorial divided by 4 factorial times 2 factorial. So that is 30. 6 factorial is, wait, that's not 6. That's not 30. It's 720. Is it? Yeah. Yep, I think because 5 factorial is 120, so 6 factorial is 6 times that, which makes it 720. And then we divide it by 4 factorial is 12. No, it's 24. And then 2 factorial is just 2. So now we are dividing 720 by 48. 15 sounds about right. Okay? So it does work out. Isn't that kind of cool? Pascal's triangle, which some of you learned when you learned how to multiply 1 times x, n times, um, kind of has something to do with combination or how we compute the number of combinations of things, which in return has to do with counting the number of items when we toss a coin, like n times, and we want m heads, out of those turns. This will tell us how many ways to get that. So all of these things are now kind of like, well, each one does not seem to be related to any of the other ones, but they do relate. Are we okay so far? All right. But this is only one step to the last thing that we want to prove. So what we really want to prove is the binomial theorem. And the binomial theorem is a little bit more complicated because it is basically saying as long as n is a natural number, which means n can be 0, p plus q to the power of n can be expressed as a sum where I goes from 0 to n, and then each term that we are adding is n choose I times p to the power of I times q to the power of n minus I. So now the question is, how do we prove that? So this is I'm just looking at the time. This is also a very important moment of this class, because in the proof of this particular theorem, I'm going to introduce a new way of proving things, which is proof by induction. So it is going to be brutal if I combine these two at the same time. If I were to try to prove the binomial theorem while introducing proof by induction, that's going to be a little bit brutal. So what I'll do is I'm going to give you an example of proof by induction using something that is, I would say, a little bit easier to deal with. All right? So I am going to give you a recursive definition of 2 to the power of n. Okay? So let me switch back to Zerno. Start a new page because I think I'm running out of room here. Okay. So we're dealing with, go back to using black ink. So we're dealing with 2 to the power n. And all of you are saying, we know how to do that already, Tak. The calculator has a way to do this. But wait, I'm going to define this in a strange way that you may not be familiar with, or you're familiar with, you just say, but why would we do that, right? So I'm going to say, if I were to write a function to compute 2 to the power of n, I'm going to write it like this, okay? I'm going to say unsigned, power 2, unsigned n, and it's going to say return. There's no conditional statement because I'm going to use a ternary expression, which is kind of like a combination of a conditional expression, conditional statement, and expressions. So I'm going to say return, and I'm going to say if n does equal to 0, return a 1. Otherwise, do a recursion. Otherwise, return 2 times power 2, n minus 1. Okay, so I'm just going to pause here because this is a recursive, unnecessarily complicated way to do it, because I'm using recursion when recursion is not really needed. But it's important because recursion and proof by induction has a very close relationship. Okay, so when you look at this, does that make sense to you? Okay, yes, okay. Um, So the next question is, how do we prove the correctness of this particular function? I mean, intuitively, it makes sense, right? Because let's just say that we're trying to compute, 2 to the power of 5, okay? So in this case, it will go to, okay, does n equal to 0? No. Then we go to here, which is 2 times 2 to the power of 4. I mean, it's 2 to the power of 5, 2 times 2 to the power of 4. Yeah, that makes sense, right? So we keep going down until we get to 2 to the power of 0, which in this case is by definition, 2 to the power of 0 is 1. And then we go back through the recursion, we backtrace it, and then we just kind of go back to the original problem. It seems to make sense. But how do we prove that this particular way of computing 2 to the power of n is going to work? How do we prove that? So the idea is proof by induction, okay? So proof by induction has 2 steps. Step 1 is what we call the basis. Step 2 is what we call the induction step. So we'll deal with one at a time. We'll deal with the basis first. What the base step or basis is trying to deal with is to say, well, instead of focusing on all the natural numbers, just focus on one specific value. Now, it would be natural for us to focus on 0, but we don't have to, okay? But in this case, I'm going to focus on 0. In other words, I'm just going to ask the question, if n equals to 0, I want to ask the question of whether 2 to the power of n equals to 1 or not. That's the question I'm asking. Why do I ask this question? It has to do with the algorithm itself saying if n equals to 0, I am going to return 1 as the answer. Is that making any sense? When the recursion stops, that is when I want to put my base case. Is that okay? So can we prove this? 2 to the power of n when n equals to 0 is 1. Well, I suppose 2 to the power of n is now 2 to the power of 0, which is 1. Okay, that's the end of the proof. In other words, the base case or the basis is usually very easy to prove because all you're doing is to say, take a number, stick it into n, do the calculation, make sure the theorem does make sense for the base case. Are we good so far? All right. So now we look at the induction step. The induction step has 2 parts in itself. The first part is the induction assumption. So we have to look at the assumption. So in this case, the assumption is assume the theorem is true when n equals to k. That's it. That's the assumption. So in the induction step, the assumption is always the same. Well, I shouldn't say always, but usually they have this format. Sometimes there are a few variations, but most of the time it looks like this. We say assume the theorem is true when n equals to k. So most people would naturally ask, so what k are we talking about, right? Is k 0, is k 1, or is k 10? Nope, it's just k. K is a natural number. That's all I'm going to say. You're like, that sounds awfully vague and flexible. I mean, is that going to work? So let's just bear with me for now. So step 2 is to say use the assumption to prove the theorem when n equals to k plus 1. Now, this is the crucial part. So far, I have mentioned nothing about 2 to the power of n because this is the template of every single proof by induction. Okay? It's just saying, make an assumption, use that assumption to prove that the theorem is true when n equals to k plus 1. Okay. Well, so far, I really have not stated the theorem itself. So let me just make sure that I state what the theorem is. So in this case, the theorem is basically saying 2 to the power of n is the same thing as if n equals to 0, then it is just 1. Otherwise, it is 2 times 2 to the power of n minus 1. I'm just looking at this and trying to determine whether that makes sense or not. Nope, it doesn't make sense. Okay. Okay. First, we define f of n being the same thing as power 2. So this one is just, when n equals to 0, return a 1. Otherwise, return 2 times f of n minus 1. Okay? So I'm defining f of n using this method. The theorem is basically saying 2 to the power of n and n, f of n are the same thing. So this part here is the theorem. Are we doing okay so far with the theorem? I came up with a function, and I claim that function is going to compute 2 to the power of n, and now I have to prove it. Is that okay? All right? So the base case is basically just saying, f of 0 is 1, which turns out to be the same thing as 2 to the power of 0, and that proves the base case. The induction step is now saying, from the assumption here, when I apply the assumption to the specific theorem that we are trying to prove, the assumption is basically saying f of k, assume f of k is indeed 2 to the power of k. This is what the assumption really boils down to. And then you guys are going to say, but Tag, you didn't say what k is, so how would we know that? That's okay. That's the beauty of proof by induction, is you can just say, you can prove one single base case, and then the induction step will handle the rest. Okay, so what do we do with this? Okay, so we now say, okay, let's take a look at f of k plus 1. So what is f of k plus 1 based on the definition of the function f? So I'm going to show you the function f up here. So based on the definition of function f, what is f of k plus 1? Well, first of all, even if k is 0, k plus 1 is going to be non-zero, right? So that means in the ternary expression, we have to go for the value corresponding to the false condition. Is that making any sense? All right. So that means f of k plus 1 is going to be 2 times f of k. Is that okay? This is based on the definition of f. This has nothing to do with the assumption itself. This is really just based on how we define f. Are we good so far? The next step is going to make use of the assumption. What was the assumption again? The assumption was assume when n equals to k, the theorem is correct, right? And specifically, if you look at this assumption here, it says f of k is really just 2 to the power of k. But that's just an assumption. But we can use the assumption here. So now we can say, since we can assume that f of k is 2 to the power of k, now we have that. And then using algebra, now we have 2 to the power of k plus 1. And that's the end of the proof. Because the induction step just has to say the theorem, I have to prove that the theorem is true when n equals to k plus 1, and I just did. And that's the end of it. And then you guys are going to say, but Tag, you didn't say anything about k plus 2 or even what k is. But that's the whole idea of proof by induction. Are we okay so far with proof by induction? Because if you have any doubt about how this works or whether this works or not, now would be a good time to ask questions. Because it is not intuitive. I would say this is even less intuitive in some way compared to proof by contradiction. Because with proof by contradiction, we can actually prove proof by contradiction itself. With this one, not so much. Yep.
Okay, so you start with a specific condition that you can prove.
Yep.
Then you generalize. So why not just prove what you generalize instead of going to k plus 1? Like, why not prove f of k? Or, yeah.
So the idea of this is to say, okay, so I'll let you guys pick a number, a very specific number as a natural number, so that that's the focus of our discussion. Pick any number.
8. 8.
8. Okay. So we pick 8 as our f of 8, right? So now we want to prove that f of 8 is 2 to the power of k. 2 to the power of 8. That's what we want to prove. Is that making any sense? Okay? Because now we have fixed to look at n equals to 8 in this case. So we look at this proof and go like, how are we going to do this? Well, one way to do this is to say, well, we know, f of 0 is indeed 2 to the power of 0, right? So why don't we make that 0 equal to k over here? So now we say, let's assume that when n equals to 0, the theorem is already proven. Because it does, okay? We just proved it. And then we can use that to try to prove when n equals to k plus 1, but because k is 0, k plus 1 is just 1, right? So now we use the definition of k to say, what is f of 1? Well, according to how we define f of 1 is 2 times f of 0, right? But we already know that 2 times 2 to the power of 0 is really, f of 0 is indeed 2 to the power of 0. So as a result, 2 times 1 is 2, which is also 2 to the power of 1. So that will help me prove the case when k equals to 1, right? And then what do? I go back here, but this time I'm going to say, assume the theorem is true when n equals to 1, because we just proved it. So going through the same process, it will basically end up proving, the theorem is also true when n equals to 2. And what do? We go all the way back here and say, assume the theorem is true because it is, we just proved it, when n equals to 2, then we get to 3, we get to 4, we get to 5, we get to 6, we get to 7, and then we finally get to 8. Is that okay? So as long as you choose a natural number, I can use this analogy to eventually get to that particular natural number. Does that make sense? Yes? Okay. So, what are the key steps of proof by induction? 3 things. One is called the base case or the basis, where you basically look at one specific value for the n, and you say, can we prove this? Okay, and in this case, it's pretty easy to do. Then we have 2 sub-steps in the induction step. The first one is to make an assumption that the theorem is true when n equals to k. What k are we talking about? Doesn't matter, okay? Just make that k. Step 2 is to use the assumption to prove that the theorem is true when n equals to k plus 1. And that's it. That's the structure of a induction proof, or proof by induction. Is that concept okay so far? Okay. So let's try to do that in 5 minutes. Okay, let's try to prove the binomial theorem in 5 minutes. And I promise you, we can do that. Okay, because once we understand the concept, it's just a matter of applying it. All right, so the first thing is we have to identify what we are trying to prove. This is the theorem that we want to prove. But this equation here, this is the actual core of what we're trying to prove. The quantifier is simply limiting the range of what n can be. So in this case, n can start from 0. It can be 1, 2, 3, 4, and so on. So the first thing we need to do is to say, well, let's go ahead and prove that the theorem holds when n equals to 0. So we put a 0 over here, we put a 0 over here, which ends up with a 0 over here, and also a 0 over here. So p plus q to the power of 0 is 1. This has to do with anything to the power of 0 is 1. Has nothing to do with proof by induction. But then we also say, what about here? We put n being 0 over here, so we actually try to expand the summation. Well, if I goes from 0 to 0, there's only one term, which is when I exactly equals to 0. So when I does equal to 0, then we end up with 0 choose 0, because n is 0 as well. That's why we have the n 0 choose 0. And then we have p to the power of 0, because we have p to the power of I, and I start from 0. We also have q to the power of 0, because we have q to the power of n minus I. N is 0, I is also 0. 0 minus 0, guess what? It's also 0. But this is also can be rewritten in the summation format. And this is how I can say p plus q to the power of 0 is the sigma of I going from 0 to 0. And inside we have 0 choose I times p to the power of I times q to the power of 0 minus I, which matches the format over here. Is that okay? Does everybody understand how I just proved the base case? Is when n equals to 0. Is that okay? All right. So assuming that is okay, then we go to the induction step. So in the induction step, we basically say the theorem holds true for some arbitrary n equals to k. And we want to use that assumption to prove that when n equals to k plus 1, the theorem also holds. So the structure of the proof is identical to the example earlier. So now what do? Well, we expand the assumption. So based on the assumption, p plus q to the power of k is this sigma term here. All I did was to use the theorem and substitute every n with k. That becomes the assumption. Is that okay? Are we good there? Okay. So now we ask, what about the case when n equals to k plus 1? So we are basically asking, what is some other way to write out p plus q to the power of k plus 1? Because this k plus 1 is where n went, okay? So we are specifically looking for one's case when n equals to k plus 1. So the first line is just making use of algebra. P plus q to the power of k plus 1, I can peel off one of the k plus 1, p plus q on its own, and then the rest is p plus q to the power of k. Is that okay? All right? And then I applied the assumption, because the assumption right here is basically saying if I see p plus q to the power of k, I can replace it with this sigma term. And that's exactly what I do here. I just replace p plus q to the power of k with this sigma term. How is that going to help us? So in the next step, I put this p plus q into the term that we are summing. So this way, instead of let me see here. I made a mistake. Nope, this is fine. So I just moved p plus q from outside to the term that I am that I'm summing over. That's the step. And then what I do is I do distribution. So this p goes along with this term, so it becomes its own sigma term. This q goes to the other term, and it becomes its own sigma term. Is that okay? Okay, so it's basically just distribution, but I'm distributing to the term that by itself is a sigma term. So I end up with this. And then from here to here is a little bit tricky. So what did I do? What is the change from the fourth line to the fifth line? This is probably the most tricky line of the entire proof. What did I do? What are the changes? Or what are the similarities? Well, let's look at the things that looks super suspicious, which is k plus 1 choose k plus 1. How did that get here? That was never here. I mean, I only goes from 0 to k. We never dealt with k plus 1. How did I introduce k plus 1 into the entire thing? But let me ask you a question. What is k plus 1 choose k plus 1? What is n choose n? What is m choose m? What is k choose k? It's going to be a 1, okay? Oh, okay, so if that is a 1, let's look at this little p times k plus 1 times q to the power of 0. Where is that coming from? Aha. We see that here. So we have a p to the power of I plus 1, but this I ranges from 0 to k. So that means for the sigma on the left-hand side, the last term has a p to the power of k plus 1. Is that okay? And at the same time, q is to the power of k minus I, but when I equals to k, q is to the power of 0. So that explains how we have this term of p to the power of k plus 1 times q to the power of 0. Okay, what about the coefficient? Does that make sense? When I equals to k, we have k choose k, which is 1. K plus 1 choose k plus 1 is also 1. Is that okay? So all I did is to pick out the last item of the sigma from on the left-hand side and pick it out to be its own term. That's all I did. Is that okay? What about the first term? What about this k plus 1 choose 0 times p to the power of 0 times q to the power of k plus 1? Where is that coming from? The sigma on the right-hand side. This guy over here. Exactly which one? Well, think of it when I equals to 0. So look at the sigma term. Okay, I can use the mouse pointer. Look at this term here. When I equals to 0, what happens? When I equals to 0, we have k choose 0. And tell me what is k choose 0? What is 1 choose 0? What is 5 choose 0? How many ways can I get nothing out of a bag of items? Exactly 1. Okay. And then the other thing is when I equals to 0, p would be to the power of 0, q would be to the power of k plus 1, right? And that's exactly what we have here. K plus 1 choose 0 is exactly the same as k choose 0. So that is the trick of how I can peel off the first item of the right-hand side and put it here, and I can peel off the last item from the left-hand side and put it all the way to the end over here. What about the things in between? Well, the things in between, I just say, don't start with the first item that we started here, start with the second item. With this one, don't end with the last item over here, end with the second to the last item, okay? But how is that going to help us? So how do we go from the fifth line to the sixth line? What did I change? I somehow managed to unify the range of k, because the range of I for each sigma. You can see how originally one is ranging from 0 to k minus 1, and the other one ranged from 1 to k. Somehow I did something so that they can now both range from 1 to k. How did I do that? Well, you can always do a shifting. You can always adjust where you start and when you end, and then you make changes of how you make use of I inside the expression to be added. Because you can see how I used to just say k choose I, now I say k choose I minus 1. So if I shift I by 1, all I have to do is to counter that shift by subtracting 1 from I. Every single time I saw I, it becomes I minus 1. Is that okay? And I do the same thing with the exponent, except it doesn't look like it because k minus in parentheses I minus 1 is really the same thing as k minus I plus 1. Is that okay? The other one is not adjusted, it stays the same. But because the two sigmas now end up with the same range, I is going from 1 to k, I can now combine the two sigmas into one single sigma. So I'm combining these two into one single sigma. The term becomes the sum of the two individual ones, but I can now combine the two. And why do I want to do that? Because this is how I can apply Pascal's identity. So now we end up with k choose I minus 1 plus k choose I in parentheses. That becomes the coefficient. What is outside of the coefficient is not as important because the coefficient itself is when I can apply Pascal's identity. So using Pascal's identity, k choose I minus 1 plus k choose I becomes k plus 1 choose I. Is that okay? So this becomes that because of Pascal's identity. So once I get to this point, I look at this and go like, oh, this is kind of cool because all the choosing, they're all starting with k plus 1 now. This is k plus 1 choose 0, k plus 1 choose I, and I goes from 1 to k. And the last one is k plus 1 choose k plus 1. Sounds like we can combine the whole thing into one single sigma again. Because this thing can become the beginning, the new beginning, so that I can change I to start from 0. And this one becomes the end when I can change the k, the ending of the range, to k plus 1. So that concludes the whole thing, because this particular format matches the pattern of the theorem. Except where we saw n, we now see k plus 1. Is that okay? So this proof is a little bit more complicated because it is using a new proof technique, which is called the proof by induction. And it's also making use of Pascal's identity. And it's also using the accordion property of these series, expanding and contracting. And the trickiest part is anything choose 0 is 1. Anything choose anything is also 1. So I think that is probably the trickiest part of the entire proof. Are we doing okay so far with this? Okay, we're running out of time, so I'm going to have you guys to enjoy your weekend and study before we have our exam 2 on Monday. So I am taking into consideration this is a pencil and paper type of test. So I will try to adjust it so that you guys would not have to write a lot. Yep.
Is this going to be on the exam?
No.
Because I looked at exam 2, there was a question about proof.
Not with the one that we went through. We talked about the exam 2 from spring 22. That one does not have proof.
Oh, no, I looked at the other one.
Oh, yeah, because sometimes I change, when we have the second exam. So sometimes I would have talked about proof by induction already, and this time I have not talked about proof by induction yet.
Hey, do you remember when I was first starting the project, and there's all those mock-up programs?
Mm-hmm.
Did that make sense at all? Why I did that?